All right, just like we did with the exponential function, we're now going to take a look at the log function, the graph, I should say, of each of these functions. So now let's take a look at the log. So the first question I'm going to ask us is, well, what's the domain of a logarithmic function? So we're going to do some shifts here. We're going to do some transformations. They work the same as they always have. We're adding 3. That's going to take us to the left 3. But the first thing we have to remember, a log of base 2, or any log, has a vertical asymptote at x equals 0. So why is this? Because there is a vertical line along the graph that it can't cross. And that is right there at x equals 0 because there can't be any negative values put in for x. Do you remember we talked about this in the last video? There's no way to turn 2, no exponent in the world. So a log is an exponent. Tell me the name of the exponent that is going to turn 2 into a negative number. There isn't one, so it can't happen. So the graph stops here, and there's no value that's going to turn it into 0 either. So we have this line here that it can never pass because it can never ever reach it. And that line is x equals 0. So that's a vertical line at x equals 0. Now, if we're asking what the domain is, so the domain of the original function is always going to be 0 to infinity because we can't cross that line. Now, we've shifted this one. So we've gone 3 to the left. So let me see if we got a picture here. Well, there's not, but let's look at the picture. So if I take the original logarithm function, I move it 3 to the left, isn't my line going to move to the left as well? And now the line that can't be crossed is negative 3. Now, so my domain would become negative 3 to infinity. So there's a visual way to see what would be happening because we're moving it to the left. A mathematical way to do it is that we know that what's inside of there has to be greater than or greater than 0. So just like when we were doing the domain of a square root, what we saw is what's underneath here has to be greater than or equal to 0. Well, here, whatever is inside of there has to be greater than 0. It has to be because of what happens here with that line we can't cross. So all you got to do is solve this to find the domain. I need x to be greater than equal, or just greater, sorry, greater than negative 3. So if we write that as a domain, it's this. Okay, now there's two ways we can think of this. This is we have the original log function being moved 2 to the right, and then 1 up. Well, you know, the 1 up isn't going to have anything to do with it. So if there was this vertical line we couldn't cross at x equals 0, well, now it's moved 2 to the right, and it's going to be 2 to infinity as our domain. Do you see what I mean? So our function is moved 2 to the right. Now the mathematical way to see this is simply this. Look at the potential problem area in this function. Well, the only problem is right here. We need this to be greater than 0. Okay, well, let's send 2 to the other side. The values of x that would make that happen, our x has to be greater than 2, which is what we saw visually, which is what we confirm mathematically. Okay, now this one gets a little crazy because this will mess with your head a little bit because of the way this is written here. But if I want the domain of 5 minus 2x, all we're going to do is solve, okay, where is that greater than 0? All right, so we're going to send 5 to the other side, make him negative 5. Now, we have to divide both of these by negative 2. So I'm going to get x, and that's going to flip my inequality sign. I get x is less than 5 over 2. Now, these are the values that are acceptable. So if I'm writing that as a domain, the values that are acceptable are those that are less than 5 halves, or 5 over 2. So that'd be negative infinity to 5 over 2. Parenthesis, because we don't want to include it. Okay, let's look at it again. Now, if you thought of it graphically, we're moving to the right 5, so you can probably already see that it's going to be 5 to infinity. But let's do it mathematically. The only thing that matters is the potential problem area, which is here. I need x minus 5 to be greater than 0. So solving that, x has to be greater than 5. These are the acceptable values. That's why that's our domain, the values of x that are permitted. Okay, now there's a couple ways to do this. We're going to take a look at the graph of a log function, but what I think is super important to see, if you remember my discussion earlier, that this logarithm and exponential, they're inverses of each other. So the exponential function and the log function, they're inverse machines. One would take you one way, the other would take the other. So if you had the exponential function and you had this dashed line here, you could simply flip the graph of the exponential over this line. Give me just 1 second here. Okay, so if I had a function, suppose I wanted to graph log base 2 of x. Well, what I could graph is simply 2 to the x, and I could flip it over that diagonal line. That would be a very easy way to do it. So let me just show you that. I don't have a ton of space here, but so remember what we would do for our key points on an exponential. If you put in 0, you always get out 1, because 2 to the 0, right? So another thing, you could always put in 1 for x, you're always going to get b, right? Now, I could graph this function. I could graph the exponential at 0, 1, and 1, 2, and I could graph that. Now, if I had a dashed line right here, I could then flip it over that line, and I would have the log function. It's going to be the mirror image on the other side of that line, y equals 0. Okay, now that's what's going on visually. You could literally do this if you wanted, flip it over the line, but here's an even easier idea. If I found the points 0, 1, and 1, 2 for the exponential, well, do you remember if they're inverse machines, the domain and the range are going to reverse. What was the domain is now the range and vice versa. So I think it's easier here to find these two key points from the exponential. If I want to do the log base 2, I'm just going to reverse them. I'm going to make the x and y switch places. Now this is very easy to graph, and just like with the exponential, these would be the only two that would be necessary for me. You could add a third point if you wanted, but so look what they've done here. So now their key points are 1, 0 and b1. Well, on the exponential it was 0, 1 and 1b, but because they're inverses of each other, you can just reverse the domain and the range. Okay, so what I would do to graph log base 5 is I would think about 5 to the x. So I know if I put in 0, I get out 1. I know if I put in 1, I get b. But this isn't 5 to the x, this is log of 5, so it's the inverse machine. So I'm going to reverse these points, and I'm ready to go. Do they have these graphed already? Yeah, so I have these graphs. So they've reversed them. Here's my two reverse points, plotted those, and I've got my picture. Oh yeah, now they're asking us some questions about domain and range. Well, let's start with the asymptote. I have inverted this, but we know that logs have to be greater than 0. So my vertical asymptote is at x equals 0. It's that line it doesn't cross. My domain is 0 to infinity. Now how about the range? If I were to take that ruler and go up this line, you'll actually cover everything. Okay, I think we have just one more here. So let's do that same trick again. What I'm going to do, I think that's 1/5 is what that's supposed to say. Let's see what 1/5 to the x would be, because I think this is much easier. So if I put in 0, I always get 1. If I put in 1, I always get b. Okay, but we're not doing that. We're doing log of 1/5. So let's reverse the domain and the range. Okay, I'm going to graph that. Oh, I don't know why it does that. It's so hard to get to do dots. Okay, so 1/5 and 1, something like that. Oh, yeah, something like that. Okay. Hold on, let me see. Yeah, I'm trying to think. Yeah, I guess it would do this. I'm trying to think what it would do like this. Okay, so that's a terrible picture, but the key was I found my 2 points from the exponential, and then I reversed them. Now, how about our domain, range, and our asymptote? Well, all we've done, we haven't done anything that's going to change that asymptote. X's still have to be greater than 0. So our asymptote is still at x equals 0. Now, how about our domain? It's actually going to go on here forever. Hold on, am I right about that? Yeah, no, I'm not right about that. Sorry. So I was right here. We have this asymptote here at x equals 0, so our domain can't cross. It's got to be 0 to infinity. But now, if we took our ruler, I know it doesn't look like it's gradually going down here forever, and it's always going up. So if I had my ruler, we would hit everywhere. And my range is negative infinity to infinity. Okay, so what I'm suggesting here is that the key in order to graph an logarithmic function is actually in something we already know how to do, which is to do the exponential function. And because they're inverses of each other, you can just flip the domain and range around and make them vice versa. So do those two key points, 0, 1, and 1b, and just flip them. Flip the x's and y's, and then you can graph the logarithmic version.